Alright, in this video we just look at section 16.3 in the context of just some things that are true in general. Okay, so let's assume that we have a 2D vector field on the xy plane. Okay, and let's say that there's some vector field given here. Okay, and let's say that you have a curve in this problem. Let's say here is the point P and here is the point Q, and then maybe there is this third point over here, R. Okay, and we will then have maybe a curve going from P to R and then a curve going from R to Q. Okay, so there are three paths shown in this problem. There's the one from P to R, and then there is the curve also from R to Q. Okay, so we have three paths. We have C1, we have C2, and then we have C3. Okay, now we know from the work integral interpretation that the integral of the vector field, okay, along the path C1, okay, is going to be the same amount of work if you were to go along two separate paths, the path from C2, right, of f dotted with dr, and then you add that to, right, the curve from C3, f dotted with dr. Okay, let me pause and fix the colors here. All right, excuse me. So we're back. I'm sorry. I've fixed the integral along the path C1, and I fixed it to be a pink color. And what we're trying to address is this equality true in general? Okay. We've seen in previous videos that one can compute line integrals along a variety of paths. Okay. And in general, right, one would like to think that if you did the integral along one of the paths, C1, and then you started at P, and then you ended up at the point Q, and then you went along a different path from C2, from P to R, and then you finished along the path C3 so that you ended at Q. Both of these paths start at P but end at Q. Start at P but end at Q. These two problems together start at P but end at Q. And the question is, will they be the same value? Did you do the same amount of work? Okay? And the answer is that in general, you do not expect these to be equal to each other. It is not known that these two integrals will be equal. Okay? But what we can say, right, we can say that we will have equality in the context of the vector field being conservative. And now we're going to figure out what it means for the function to be conservative. So, but what if the vector field is the gradient of some function phi, a potential function? Okay? It will, so this is also called the vector field being conservative. And this is why we're going to, in this example, we'll see what it means, why the word conservative is used. Okay? If the vector field here that we are choosing is not just any random vector field, but a vector field that is the gradient of some potential function, then when you compute this integral here, the integral along the curve C1, right, that line integral will be, from the fundamental theorem of line integrals, the potential function at Q minus the potential function evaluated at the point P. Okay, and the question is, was that equal to the second line integral, which is the vector field along the curve C2, which will be the potential function at the point R minus the potential function at the point P, right? Now, if we bring on that third integral, the integral along the path C3, will have the potential function at the point Q minus the potential at the point R. Okay, and we can see here that the potential functions at R end up canceling each other out because of the plus and minus sign, and then we'll get the potential function at Q minus the potential function at P, which in fact is equal to the other side of the integral. So one thing we can say is that it is true, it is known that the integral along the curve C1 is equal to the integral along the path C2, f dotted with dr, plus the integral of f dotted with dr along C3. Okay, that will be equal if the vector field is conservative, or that there is a potential function. And so what we can see by conservative is that work is being conserved, that the amount of work to go from P to Q, and then the work along C2 path and then C3 path, that will be the same amount of work. And that is why we're using the conservative language, that if a potential function exists, then the field is conservative, which means that it doesn't matter which path you go along between 2 points, you will get the same amount of work done. And that is a very important observation and it's a very important result of a function being conservative, the path independent nature of the line integrals if the vector field is conservative.